Okay, yeah, so good morning. So yes, today we then go on from a bit different angle and think about particles. And the motivation for this is that there are many phenomena in cosmology that we like to think about in terms of particles. So, for instance, neutrinos. And then neutrinos, we could think about the normal neutrinos, the left-handed neutrinos, or also right-handed are quite important in cosmology. Then dark matter, say, we don't know what dark matter is, and so it's not a guarantee that it's sort of particle-like, but still most of the models that are somehow simple and attractive maybe are particle-like dark matter models. Also baryon asymmetry is one of the big issues in cosmology, and of course baryons are particles, protons, neutrons, and so forth. And so, okay, so now when we discuss these issues, then somehow there's a common tool that we often like to use, and that tool goes under the name of Boltzmann equations. But then somehow when one first meets Boltzmann equations, it's a little bit maybe confusing because, well, first of all, obviously Boltzmann equations are, at least in their original form, they are even older than quantum mechanics, not to mention quantum field theory. So if we are still using them today, then the question is, what is it from the modern perspective? Is it some model? Or is it like an effective theory that we could derive from quantum field theory? If it's an effective description, then it's never exact. So what is the small parameter in the Boltzmann equations? And these are all very kind of difficult questions. There's not a very clean answer to them. However, I mean, presumably it's a good tool because so many people are using it. So what I'm trying to do today is basically two things. It's not a comprehensive answer to all these questions, which may be confusing, but like first what they are. That's one thing, and then maybe like the a little bit conceptual goal is how they might arise from quantum field theory. Or thermal field theory. So that at least we then know that there is some relation to thermal field theory, to fields, to the kind of things that we discussed yesterday. Okay, so that's the goal, and now however, I want to start from really like a very simple, like it is really like a textbook consideration, but again, many of these sort of non-equilibrium things, they are at the end of the textbook often, so maybe in a normal lecture we would skip it or we didn't have time to go through it. But the basic consideration, it goes back to Boltzmann, and it has a name which is called the H theorem. And so somehow it probably was famous at some point in the history of science. Nowadays maybe not so famous anymore, but it is sort of a simple picture and helps us to at least understand what the Boltzmann equations are trying to do, and then we write down the actual Boltzmann equations. So what's the H theorem? So let's think about really like a quantum mechanical sort of a Hilbert space. And I put here an axis, so this axis is just like an enumeration of the different states in my Hilbert space. So there are different states here. State I and somewhere else a state I prime. And now we assume that it's a complicated system, so we don't know exactly how these different states are occupied. And so what one does learn often in quantum mechanics and statistical physics is that if you don't have complete information, then you can represent your information, the incomplete information, in terms of a density matrix. So we take all states, and then we say that we have some probabilities that we are in the different states. And that's then the density matrix. So it's kind of in this language that we are now thinking. So we have these states, and we say that there's a certain probability that we are here, there's a certain probability that we are here, and for all states there's a probability. However, now the system is evolving in time, and this means that one can also go from one state to another state. So I can go from state I prime to state I, and we associate a rate with this transition. So rate from I prime to I, and vice versa, I can go from I to I prime, and with that also we can associate a rate from I to I prime. I write the indices such that it's from the rate from the first to the second. So now, however, microscopically we then know in the modern language of quantum field theory, we know that most processes there is time reversal invariance. So let's say microscopic time reversal would say that if one process is possible and goes with some rate, then the other process should also be possible and go with some rate. So we say that actually these two rates are the same. Okay. So then it would seem that nothing is going on, but that's not the case. So now what then H is, what Boltzmann defined is a quantity which at first it's just a definition, maybe sum over all states, and then the probabilities times the logs of the probabilities. It's kind of a quantity. Of course, today we would recognize this. We say this is like the entropy. So more precisely, it's the minus the entropy divided by the Boltzmann constant. And this well, there are many entropies. This is the Gibbs entropy. Okay, so now we already kind of anticipate that somehow this H theorem has to do with the arrow of time and with the increase of entropy. And that's indeed where we are going, because what we now want to do is so first of all, we write down an equation for how these probabilities might evolve. So if there are these rates, then they should evolve somehow. And so then there is now an equation, and often one calls this equation a master equation. It makes it sound very prominent, but it's really like a simplest equation you could write, which says that suppose that we think about what happens to this probability here. Pi and dot means I take a time derivative. So what can happen is two things can happen. One thing is that you take probabilities in all the other states and you sum over all the other states, I prime, and you take a probability, for instance, in the state Pi prime, and then you make a transition from that state to our state. So then the probability here can increase because you can go from somewhere else to here. And so this is what is called a gain term. We gain probability. But then also the opposite can happen. I can be here and I can go to any other state. And then the probability decreases, so that comes with a minus sign. And so now this rate is, however, it's proportional to this probability Pi. If I'm asking what happens to this, then if I'm going away, is proportional to this. I mean, if the probability of p here would be very small, then also the rate would be very small. There's so to say, nothing left to lose if we are already not there anymore. So, in other words, this is proportional to the pi, and then the rate from I to I prime. So a very, very simple equation, and this is the loss term. And of course, this equation is even simpler because I made this assumption, so I can really write this as I can write this as pi prime minus pi gamma I prime. And now we look at then what happens with the h. Now it's a yeah, so to say trivial computation, but still not quite trivial. So okay, we can take a derivative in the pi, or we can take a derivative here. Then we get 1 over pi, which cancels the pi in front, but then there's the inner derivative. And now I then insert the master equation. So then there is a twofold sum. We can take the gamma here. So first term is then pi prime ln pi minus pi ln pi plus pi prime minus pi. So not so transparent, and now the trick is simply there are two sums, so we symmetrize the sums. So I write it like 1/2 and the sum, and then every term I duplicate. So pi prime ln pi plus pi ln pi prime minus pi ln pi minus pi prime ln pi prime. And then there is this term, but this term disappears when I symmetrize because it's antisymmetric in the I prime I. It just disappears. So then I have only the log terms. So now, okay, now I take this in front here, and then I pull one of the p. Let's say I pull this pi also here in front, and then let's see what. Then I first take these terms with the pi. I pull the pi front, and then the remainder is log of pi prime, and here there is minus pi, so pi prime over pi. So these are these terms, and then there are the other terms, and one is with log pi prime, and then there's this one with log, so these are the opposite signs, so I can write it like this, but it comes with a minus sign. And since I pulled this in front, then I have here 1 minus pi prime over pi. Okay, so now it still looks a bit weird, but now we notice there's a function here, and if I denote pi prime over pi by x, then this is the function 1 minus x log x. And a simple function of which we note the property that this function is always smaller than or equal to 0. Because, okay, if x is larger than or equal to 0. Because, okay, these probabilities are positive, non-negative, so x is larger than or equal to 0. If x is less than 1, then this is positive, but log is negative, so product is negative. If x is more than 1, then this is negative, but the log is positive, again, negative. The only case where I get the equality is if x is equal to 1, then this is 0, this is 0. Okay, so what does it mean? This is less than or equal to 1, pi's larger than equal 1, rates larger than equal 1, equal 0. Larger than equal 0, less than equal 0, less than equal to 0, less than equal to 0. That's the H theorem. The H function always, it cannot increase. It decreases, and correspondingly the entropy then increases. And so this is the famous, arrow of time related to entropy, if you wish. Okay, so that's the general statement. Now, a particular state of the system is then what we call the equilibrium state. And the equilibrium state is by definition the state where H prime, S prime is 0. Entropy is maximized, so derivative is 0. So to say, macroscopically speaking, nothing happens. Okay, so when do we achieve this state? Now, this state can only be achieved if we have states which can transition to each other, so that these gammas are actually not 0 but positive. So if this is positive, and if some of these states are occupied, so these are positive. So if these are positive, then the only possibility that I get 0 is if this is 0. And this is 0 only when x is 1. And x is 1 only when all the probabilities of the states that can talk to each other are the same. So that's the only solution. And so this it's an important statement in statistical physics that if I have states which can transition to each other, they must all be occupied with the same probability. And this is known as the ergodicity. One of the basic postulates. You can also almost take this as a definition, as an alternative definition of equilibrium, that if all the states that can be occupied, they are occupied with the same probability. That's ergodicity. Now, out of this follows then, now we go back to what we had in the beginning, the master equation. The master equation, it then follows that pi prime is, well, if the probabilities are the same, then the pi prime is 0. So probabilities are the same and they don't change. Fine. Now, however, the important thing is that this 0 is not 0 because everything is 0. It's really a 0 because of this cancellation. It's a cancellation between these two terms. The gain term and the loss term. And so these are both non-zero. So equilibrium is not a state where nothing happens. Actually, a lot of things are happening all the time. There are many gain processes taking place, there are many loss processes taking place, but they just exactly cancel each other. And that's another important concept in statistical physics that's called the detailed balance. and detailed balance is then, it's not only important for statistical physics, for instance, detailed balance is very important for, in many, let's say, numerical simulations. If you want to be sure that you are doing a correct simulation, you have to make sure that your algorithm is doing processes in one direction, but also in the other direction. Otherwise, you're stuck in some wrong region of the path integral, so to say. Okay, so good. So that's kind of the background. So very basic things. And now we then go to the actual Boltzmann equation. So the Boltzmann equation then now is an implementation of this more abstract philosophy in that we then replace these probabilities of some states. We replace them by a phase-space distribution. So Fi at time t point x momentum p. So, and this is particle species. Now instead of state, we talk about particle species. So different types of particles, and then this is a phase-space distribution. Again, it may be a little bit confusing at first sight because, I mean, we were talking about these states I and I prime as if they were really like states in some Hilbert space. So that sounds quantum mechanics. Now, when we go to phase-space distribution, that is very classical. Sounds very classical, and it is. But still, there is a relation because this was not, so to say, full pure quantum mechanics, because we were already in the statistical description that we didn't have full information about the system. We had the density matrix, and we were already talking about probabilities there. And the phase-space distributions really are, it's the probability of occupying some region of the phase space. Somewhere in space we have a certain momentum, and the f tells how likely it is that we are there. Okay, so now this is the general phase-space distribution. In cosmology, we simplify things a bit. It's still complicated enough. One thing is, if we assume that the system is homogeneous, then this means that we can drop the x. Okay, maybe this is not always the case if we are studying something at the late stage in cosmology when we have, I don't know what, galaxy clusters or something, then it's not homogeneous. Then this is not a good assumption. But in an early universe, this is usually a very good assumption. And also we assume isotropy. And so this means that instead of a vector momentum vector, I would assume that this depends only on the absolute value of the momentum, so which I denote by p, like yesterday. Okay, so now that's then our variable. So different particle species, they can evolve in time, and they have momenta p. Okay, so first question, why do they evolve in time? Because we just said that if we are in equilibrium, then the system should be, the probability should stay fixed. And if this is the probability, then also the phase-space distribution should stay fixed. Well, this is because we are we are now doing cosmology, so we are always we are always being driven out of equilibrium, whether we like it or not. That happens. That happens because of the expansion. And so what it means is, now we write the left-hand side. So to say left-hand side of the Boltzmann equation, left-hand side is then just a time derivative. So it happens because of the expansion. Because of the expansion. Because of the expansion, everything expands, so also our momenta redshift. So if I write here a momentum, I should really think of it as like some momentum at, let's say, time t0, but then it redshifts. It becomes smaller, so it's inversely proportional to the scale factor. And if I take a time derivative, this is the total time derivative, really what happens to this function in time. And so then we have to account for this dependence here. And so now it's elementary arithmetics, but we get the partial derivative with respect to the time, and then we get the derivative from here, which is the derivative with respect to p, and then the inner derivative. And so this is then p t0, but then minus a t0, a squared t, and then the a dot t. And this I can write as, now I take the combination that appeared here already is my minus p, and then what's left over is a dot over a. A dot over a is our h, our Hubble rate. So therefore the left-hand side is dt minus p h dp of fi. And so again, if the Hubble rate were 0, then this term wouldn't be there, but because the Hubble rate in cosmology is non-zero, then this term alone, it drives us to do, it kind of enforces us to do something if we want to stay in equilibrium, let's say. Okay, then the right-hand side. So usually we write then the right-hand side. The right-hand side is where these gammas play a role. The gammas are the transitions, and in particle systems, these transitions are really collisions. So usually we call the right-hand side then the collision term. We often write it like this collision term of the Boltzmann equation. Okay, and so now how does it look like? So now now we should, okay, so let's draw kind of a diagram. So we have I'll now denote kind of, let's follow one particle species. For instance, let's say the dark matter or what neutrino that we are interested in. So I'll call it our particle species. I'll denote it by I equals 1. We are number 1, particle number 1, particle species number 1. Okay, so then we have processes, and processes are, particle physics are scatterings, and so one possibility is that we take some particles here, going somewhere and scattering. I denote this by from I to n. They have momenta q I to qn. And then out comes, let's say, our 1 with p1, and then some other particles that we maybe, which are also there, but maybe not so important for us. I'll call them PA to PM. So this is again now a gain process. Some particles come together and then they produce our particle. This is a gain term. But now, just like in the master equation and in this general picture, if this process is there, then also the time reversal, time reversal is there. So we can also have the process that, but instead our particle goes away and we have the loss. And what we will assume is, again, time reversal invariance on the microscopic level. So actually we will assume that here I now use same language as we would use in quantum field theory, so scattering matrix element. And here I have from I to n particles going to 1 plus m of these other ones. Squared is the same as in the other direction, 1 plus m going to n squared. Okay, so now with this picture in mind, I will just write down the Boltzmann equation and then explain the different ingredients in it. So the Boltzmann equation, or more precisely the right-hand side, looks a bit complicated at first sight, but it's not so complicated. It has some a bit mysterious looking factors. We'll come back to that. Then there's an integral, phase space integral. Then there is this matrix element squared. And then there are terms which represent this picture here. So first there is a gain term, and the gain term has the phase space distributions from I until n, and then there are the final states. Now, final states, if we were in vacuum, final states are just there. If it's allowed, they are there. But if we are in a medium, then the final states also matter, because if we have a boson, there is both an enhancement, 1 plus. If we have a fermion, there is Pauli blocking. If the state is already occupied, you cannot go there. Minus. So 1 plus minus F1, 1 plus minus Fa, 1 plus minus Fm. That's the gain. And then there is the loss. So minus the opposite reaction. And then we have all these particles in the initial state. So F1, Fa, Fm, and then all the other particles in the final state, but now then they have the same enhancement or blocking. Okay, and I think that should be it. It's kind of an equation. So now let me explain the different ingredients. Okay. Some of them are a bit annoying, but we shouldn't get stuck with them, and ultimately they can only then be justified really well by deriving this equation from somewhere, like I will sketch it then afterwards. But for the moment, the first thing which is a little bit maybe annoying is C. Well, C is often we write it like 1 over, and it, let's say, some number of particles in the initial state might be identical particles in the on the side of the Q's, and then, well, I don't know how to call it, IA, and then some guys might also be identical on the final state side. And now the problem is that here one is really integrating over, I haven't specified this yet, but one is integrating over all these momenta. So our momentum, the P1, that we are not integrating over, because that we are tracking what happens to this guy. But all the other momenta we are integrating over. But if there happen to be 2 identical particles here, and we are integrating over both momenta, then we are kind of double counting, because in quantum mechanics, if you exchange the momenta, it's not a separate state. You cannot identify the particles. So that's why there's kind of a symmetry factor. Because you integrate, you have to pay a price. You have to divide away the overcounting. Compensate for overcounting of identical particles. In some sense, this is where we see we are kind of taking a classical equation, but then we are using it in quantum mechanics, but then we have to do sort of fixes here and there to make sure that it's correct, but that's how it is. Okay, the factor 1/2 you cannot really understand like this. This really comes from somewhere, and so let's not worry about the 1/2 there. 1 over E1, well, that you can kind of understand because it more or less has to be there because, why? Because the equation as we have written it doesn't look covariant. And there's time derivative and there's an energy, but if you imagine that you had written something covariant like K dot D, where K is, let's say K1, better write P1 dot D, where P1 is my form momentum, then this would have E1 dt minus P1 dot nabla x1. But we have assumed homogeneity, so this term is not there, but this term would be there, and now it would be covariant. But normally we write just the time derivative, but then we have to divide by the E1. So that's a reflection of the covariant structure. So that's fine. D phi 1 plus m n, that's a phase space integral. So that's a product of all the initial state particles 1 to n, d3qi 2 pi cubed and 2 times ei. Well, of course, here one sees the same type of factor, so maybe the factor of 2 is also not so weird after all, because it's also in the normal invariant phase space measure, and here are the corresponding energies. But we also have to, this is what we normally, in scattering, we just integrate over the, well, if we scatter some particles, we can, well, it depends on what is fixed. So in scattering, we fix something and something is, the rest is not fixed. if we fix the initial states, we may integrate over the final state momenta. But here in the Boltzmann equation, we are really integrating over everything. So not only the initial states, but also all the final state particles which are not the ones that we are interested in. So A1 to M, D3, BA, to EA. Okay, that's the phase space. Well, it's not yet complete because one also has to remember that in the phase space there's energy momentum conservation. P1 plus PA plus PM minus QI minus QN. Total energy momentum conservation. And then we still have 1 plus F is Bose enhancement for bosons. And 1 minus F is Pauli blocking. For fermions. Okay, and the M, I think I already said, this is the matrix element, so I don't need to write again. So that's kind of the equation. And now, of course, if we, let's say, if we didn't know anything, then all of these functions would be unknowns. Then we would write the Boltzmann equation not only for our particle F1, but for all the other particles as well. So we would have a coupled integral differential equation for many, many phase-space distributions. It's a complicated system, but there are circumstances where people try to solve something like this, maybe not all, yeah. And yeah, so it is studied. But again, I mean, I should stress that we haven't, it's not, even if you were able to solve the Boltzmann equation for all the phase space densities separately, it's not, we haven't proven that it's still like a full description of nature. I mean, we have just postulated it out of some principles, and it looks nice, has lots of physics in it, but the validity is still to be established. So now, maybe going a bit in that direction, now we make some kind of checks about this equation. And the first thing I want to do, it's very important, is that we check detailed balance. What does it mean? It means that if we put all the particles in equilibrium, then nothing should happen. I mean, both these terms are there, they can be large, but they should exactly compensate for each other. So this means that we replace Qi, let's say, we replace it by Bose distribution of the corresponding energy or the Fermi distribution of the corresponding energy, depending on whether it's a boson or fermion, this particle. So now, let's look at what happens to 1 plus. So suppose it's a boson. So then we look at 1 plus NB, some energy. And so e to beta ei minus 1. That was our Bose distribution. Now I just put them together, these terms. The first term I have to write then the same thing upstairs. And then I have a plus here, so it cancels. So I have e to beta E1 times the Bose distribution. And then I do the same with the Fermi distribution. Fermi distribution we didn't see yet, but I suppose you all know that it is just the same, but with a plus sign here. And then I again put the terms together. There's 1, so I have to put 1, and then now it's a minus. And again these terms cancel, and again I get e to beta ei, Fermi distribution of ei. And therefore, I'll just remove the first line first. Therefore, what we have is that in this term, we can write everything like, whether it's boson or fermion, doesn't matter. It's always the e to beta, E1 plus EA plus EM times then the corresponding distributions without any ones plus minuses. And we can do the same here. It's exactly the same applies. So again, I should stress, this is not if we have unknown functions here. It's only if we are in equilibrium, if we are in this situation, so in equilibrium. In equilibrium, this one also becomes e to beta ei plus en times fi fn. Okay, maybe I should improve on the notation. In equilibrium, often we say that then this means that fi goes into fi bar. Sometimes we use bar like for the average quantity and then the deviation around it. But in the Boltzmann language, we may also use the bar to say that it's the equilibrium value, and then there's something on top of it or below it. So in equilibrium, I would then get these bars here. Everything would be barred. And this would also be barred. And now we just see that it's all the same. Fi, Fn, F1, Fa, Fm. Every term has the same product of the distributions. And then once I have this guy, and then I have minus the other energies. But these guys exactly cancel because we have here energy conservation. Well, we have energy momentum conservation, but as a part of the energy momentum conservation, there's energy conservation. So this cancels because of energy conservation. Okay, so that's good. So now we have established very generally that without knowing anything about the matrix element squared or what the particles precisely are or what kind of physics we are considering. If the system is in equilibrium, there are many processes taking place, but they exactly cancel each other, and that physics is correctly incorporated in the Boltzmann equation. Okay, so now I want to do another small consideration, which is that now we go then close to equilibrium. Not in equilibrium, but close to equilibrium. And so this we can call this linear response. And so this is a situation which is quite frequently the case. So for instance, we can say that all the other particles that we don't worry about, they could be things like, I don't know, gluons or something strongly interacting. And so there we can say with a fair confidence that all these other particles, they are in equilibrium. And maybe also the final state particles, all the other ones, are in equilibrium. But our particle, the one we are interested in, which is maybe the dark matter particle, or the neutrino which is decoupling from the photon plasma, that one is well, we are interested in precisely because it is falling out of equilibrium, or it never entered equilibrium in the first place. So this means that our F1, then, our particle, that is not in equilibrium. We can still, so in this linear response, we are assuming that it's close to equilibrium. And so that's then an assumption about the initial state. So we say that this is the equilibrium value plus a deviation. It's like, it is perturbation theory, some average value, so to say, plus perturbation. In our case, the average value is defined in this regime, is defined as the equilibrium value. This is quite a reasonable assumption, indeed, in many contexts. So for instance, neutrino decoupling. For a long time in the history of the universe, the neutrinos, our well-known active neutrinos, they were in equilibrium. And then at some moment, the rate which keeps them in equilibrium just becomes too slow to keep them in equilibrium after that moment. But until then, they are in equilibrium. So we can study this decoupling by writing their distribution like this. It's equilibrium and then a small deviation, and then we solve for the deviation. And so you see now the problem it's really solvable because all these functions are known functions for both our Fermi distributions, and we only have one function which is not known. So then we have just a differential equation for one function. Well, it's still a partial differential equation. You remember left-hand side had dt and dp, so partial differentials. Right-hand side has an integrals. And so it is a partial differential equation in time and momentum, but still only for one function. So what happens if I take this and put it into the Boltzmann equation? Two things happen. The leading term leading term is this one. Well, we know what happens with the leading term. The leading term cancels. There's because of detailed balance. If I assume that also this one is in equilibrium, then the right-hand side drops out. So then the contribution must be proportional to the next to leading order term. And so therefore, this term then has the structure that it is proportional to my deviation and then higher order terms. And now the proportionality constant here, this we write here a gamma. And this is now a gamma in exactly the same sense as we had gamma yesterday. So it's some equilibration rate. It says how fast this particle is trying to go back to equilibrium if it falls out of it. And then one still has to think about the signs. And here the sign is minus. Why is the sign minus? Well, this is also related very much to what we said yesterday. Let's draw here a figure. This time, to make this figure simple, for a second I will again omit Hubble expansion. Then I have here somewhere the equilibrium value. And why the sign must be minus is that if I start from excess, if my delta Fi is positive, I'm above the equilibrium value, I'm somewhere here, then we expect that we go towards equilibrium. That's what the Landau theory says, that's what our everyday experience says. That's the case because the equilibrium is really the state which is the most likely one. That's the state which is at the given boundary conditions, equilibrium states are the states which are most available in the phase space. So we go towards it. So that's why there has to be a minus sign. We go towards it. If we are below it, then we go towards it. If we are below it, then this is negative, and then we have to have a plus sign so that we go towards it. And so then we go towards the equilibrium. And now you may ask, and a very good question would be, why did I draw kind of fluctuations here yesterday, but today I'm not drawing any fluctuations here. I'm just drawing towards the equilibrium. Well, the reason is that this phase space distribution is by definition, it's not the fixed value, it's a probability distribution in momentum space. So since I'm drawing a phase space distribution, which is a probability distribution, then even if the phase space distribution has a certain functional form, there are still fluctuations there, namely the equilibrium fluctuations. And the equilibrium fluctuations are contained in this equilibrium F1, and they are there. But the non-equilibrium part goes away by this linear response type of relation. Okay, so now sort of the logical step would now be to take this, what I wrote here, and really insert it here. And when I insert it here, then of course the structure here gets a bit modified because almost everywhere I put in the equilibrium value, but then the F1s I have to put in F1 plus delta F1. And the delta F1 then afterwards I pull out, and it appears here. And then the rest is inside. And so the structure afterwards, when I take out something about the F1s, it's not exactly the same. The F1 no longer appears in the integrand. It's outside. But still, it kind of has this characteristic structure, the integrand, that there are always gain terms and then there are loss terms. Okay, so now that was kind of the fast introduction to the Boltzmann equation. Maybe there are questions at this moment. Everybody is familiar with Boltzmann equation. Well. Good. So now we want to then yes.
Repeat why when we have this linear response we had F1 and then we had little part delta F1. Why it's not k times F1? You explained the why it's a very small value. Can you repeat that part again?
Somehow I didn't hear. Why? Yeah. So this is okay. So this is the assumption. A linear response means that we looked at the system to not in equilibrium, but to leading order in deviations from equilibrium. Linear means just that to linear order. Why it's also called response, that's, one doesn't see it so immediately from here, but this linear really means that we are looking at deviations from equilibrium at leading order in those deviations.
You mentioned something about the differential equation, like the, sorry, equation.
Yes.
That part.
Yes, okay, partial differential, I can still write the equation. So if we do, if we put this into the Boltzmann equation, then we would get the left-hand side dt minus p1h dp1 f f1 dp1 is minus gamma delta f1 delta f delta f is f minus f1 bar. So gamma minus, yeah, so I write it like this, f1 bar minus f1. This is now my unknown function. It's a function of time, momentum. This is a partial differential operator acting on that. I should know the Hubble rate. Then I have here a partial differential equation acting on a function of two variables. This one, the gamma, is when I insert this expansion on the right-hand side of the Boltzmann equation and I expand to linear order. Then I can extract this gamma. The gamma will then be a function of the P1. And then I have this difference. So I would have to compute this. I integrate the right-hand side of the Boltzmann equation, I compute this. Then I have f1 bar. That's a known function. That's the equilibrium function. Also a function of P1. And then there is again the unknown function. This is now my unknown. This I must compute. This is known. This I have to know. I have to know the expansion of this history of the universe. Yeah, so known. And so now it's a partial differential equation for this one unknown function. And okay, and then this one can then discuss, but actually one can turn this partial differential equation into just a thing which is called the method of characteristics. So one can, so to say, we are trying to solve this in this some plane. Now it's a partial differential equation in this plane, but instead we can integrate along some trajectories. So then we can turn it into a normal differential equation. And it's a whole topic of its own how one solves this kind of thing. Good. This is incidentally again our gain term. This is the loss term. Okay, so now we kind of completely change tools, and we want to pose the question of how could this be derived. From thermal field theory. Okay, so now it is, let's say, a general derivation is is very difficult, it's probably impossible. I mean, it's known that there are circumstances also when the Boltzmann equation is just not valid. It doesn't have all the information in thermal field theory, but this I will now more precisely refer to this as Boltzmann in linear response regime. So it's something that follows von Boltzmann, and then it follows also from thermal field theory, and we can see that from these two different things we get the same. It doesn't guarantee that the two things are the same, but they lead at least in a certain limit to something equivalent. That is then quite helpful in practice because that gives you a lot of intuition about what might be also happening with the full Boltzmann equation. I mean, if one wanted to then improve also on the full Boltzmann equation, at least it gives constraints that now we know how it has to look like in these limits. And that tells us quite a bit about also the full Boltzmann equation. So how do we do that? So now this is now somehow like if we did everything from A to Z, it's really like a long story. And what I will take some shortcuts, but what I claim is that we can compute something which I've denoted by gamma. So it's gamma. And however, in thermal field theory or also in normal quantum field theory, there our gammas they are some kind of widths. So this will be a width. So one, and there's some normalization, and then it's a width, which is an imaginary part of some correlation function, imaginary part of pi. And now I will, previously we denoted the momentum by P1, but for the following, it will be convenient to denote the momentum by K. So I denote it by K. K is omega. This is my 1 over, so to say, 1 over E1, and the spatial momentum. This is sort of the notation we had yesterday. And we will do this. Now how do we do this? We have to do this at finite temperature, and we will do this with a particular formalism, and so do this with what we called yesterday the Matsubara. And the Matsubara is also called the imaginary time. Formalism. Okay, so what we know from yesterday is that this implies that when we have propagators, then these propagators really are sums. But what we gain by that is that then the propagator looks more or less like in normal quantum field theory, just 1 over omega n squared plus k squared plus mass squared. In fact, it's even kind of nicer than in normal quantum field theory, because in normal quantum field theory you have here somewhere you have minus signs and then you have plus minus I epsilon Feynman prescription, and you have to remember all the signs correctly. Actually, this is very nice, this formalism, because everything is just like, everything is with plus sign, everything is positive. So it looks nice. The price you pay is that you have to carry out some sum. Okay, so this is kind of the simplest way that you can see that something like this could play a role, because this we derived, and then there was the exercise to show that it's like this. There's also like a derivation of this formalism, but we will not I will not go through it really in detail, but I just recall the basic ingredients. The basic ingredient is Feynman path integral. Feynman path integral says that in quantum mechanics, if we have a field and then we put in a time evolution operator, then Feynman says that this can be expressed as a path integral over all fields where the initial field at the initial time is the initial wave function, so to say, initial state, and final field is the final state, and then we integrate over I. Here is plus I, and then the action. The Lagrangian here. This is Feynman. Now, what we want is we want trace. We are interested in things like z pi is trace e to minus beta h. But now we can imagine that we do the trace in the same basis as Feynman. So in the eigenbasis of the field operator, trace can be done in any basis. If we do the trace in that basis, then we have to trace, and trace now these states are functions. These are functions in space. So we have to integrate over all functions in space, and then we take a trace. So trace means that you take some state and you take some state, and it's the same state at the beginning and at the end. So it's like the Feynman path integral, but we have to start from somewhere and come back together to come back to the same. And then we see that this is almost the same as here, but not exactly, because here there is an I, here there is no I. And so we have to also do some kind of a wick rotation. From this time, or from this time, we have to wick rotate to something else. And that something else is what we call the imaginary time. And then we have to remember that we have periodicity. And so this means that now, actually, we have this time, which usually the imaginary time we call it tau, to not confuse it with the physical time t. And then we come back, and the interval that we go is the beta, is 1 over temperature. But then we come back to the same. And this means that effectively we are living on a periodic direction. And And yesterday we learned that if we had 1 over L sum of n, it went over into dk over 2 pi when the k was 2 pi over L times n, when we were in a periodic spatial direction. So now we can do the same in the opposite direction. So normally we would have an integral over frequency, but if we now go in the same direction, and now we realize that our periodicity is L goes into beta, its inverse temperature. Then out of 1 over L becomes temperature. And so then we go from this, now in time 1 over L becomes temperature, and then there is again a sum, and the sum is now over something like this, which we call omega n, and omega n is just like here, except that 1 over L is T and n is an integer. And so these are exactly the same Matsubara frequencies as we had here. Okay, so that's sort of that would be a way to derive this imaginary time formalism by comparing these integrals and doing carefully the weak rotation. But we will not spend more time on that, but now I want to formulate then a problem so we'll take a model. We take a Lagrangian, and in that Lagrangian we put a field, our field phi, there's a coupling, our field phi, and then we put some other fields there. Doesn't matter what these other fields are. But it's a coupling like this. This field, our field phi, couples to some other fields. And now we would compute the self-energy of this phi. So diagrammatically, it's simple. I take this vertex, and then I make a loop out of these other guys. And then I have this, the phi again. Phi here, chi1, chi2. I put here a momentum k, and then I put here a momentum p, and here I have a momentum k plus p. And so now this is a simple scalar field theory, and actually I can write down what this is. I can draw a diagram, but I can write down now what it is. So in this imaginary time, it's really simple. So, okay, there's a vertex here, so it's g squared. And then there is this, what in vacuum would be an integral over the momentum p. But now, in this thermal case, everything, the integrations over omega, over the frequency, over the energy, they get replaced by these sums. And so instead of an integral over p, we have something that we denote usually by a sum integral, like this. And this is simply t sum over omega n, and then with the spatial momentum we have a normal integration. And then we just need to put the propagators here. So for the, let's take with the number 2 first, because maybe it's simpler. The propagators are simple. So for capital P, it's just like there, but now there is a frequency, I denote it by Pn squared. Then there is the spatial momentum P squared plus the mass of this guy, so m2 squared. And for the first chi1, there is k plus p. So k has, my k has omega n, so then the frequency is omega n plus pn squared, and then there is a momentum k plus p plus m1 squared. So at this moment there's nothing, it's almost well, it is a one loop diagram. So of course, one loop diagrams are never trivial. One has to work them out. But otherwise, just writing it down is not more complicated than in normal field theory. It's simpler in a sense because everything is positive, everything looks nice, there are no cuts, no poles, no nothing. And what we would like to do actually is just to carry out the sum. We would leave the integrations for later. And now I leave it as an exercise. It's a nice sum. Well, this was one exercise, but now we have a sum where we have not only one structure, but two structures. But remarkably, this sum, even though at first sight it looks a bit scary, it's doable. I mean, in a closed form. It's a convergent sum. There's nothing there, you can do it. You can even do it numerically if you want to check afterwards. It's doable. It's a simple expression. So exercise has many parts, well, a couple of parts. Carry out sum T, Pn, 2 pi nt. Then weak rotate So the only price we pay for this simplicity of the imaginary time formalism is that afterwards we have to go back to Minkowskian. So this means that afterwards we write this Matsubara frequency of the external leg omega n as minus I omega plus I0 plus. This is the weak rotation from something we rotate like 90 degrees. And then when we go Minkowskian, there's always something like the Feynman description. This is actually not exactly the Feynman description. This leads to some other. It's not a time-ordered correlation function that comes out. It's something time-ordered in a different way. But still, once you do a weak rotation, there are always poles and cuts in the plane of your energies. And to specify what you are exactly doing, you have to say how you circumvent them. And this is the thing to do. And I'm not explaining why this is the thing to do. I'm just stating it's the thing to do. And then you take the gamma is the imaginary part of this over omega. So it's kind of it's a very nice computation, and it's not. If you would know exactly what to do, it would be like one page. If you don't know, you can easily spend more pages, but yeah. But I'll tell you what the answer looks like. The answer, of course, looks exactly like the Boltzmann equation. The answer looks like as follows: g squared from the vertex 2, this mysterious 2 that we had comes out from there. Omega is here, and then there is a phase space integral d phi. And now we have 3 particles. And so I'll write it like 1 to 2 integral comes out. Okay, we had previously in the Boltzmann equation, we have matrix element squared, but now the matrix, this is a scalar theory, so the matrix element squared is really like this g squared, it's already here. Okay, I should actually, I should be more careful. I write this as integration over p, integration over q. I write here 4 times EP EQ. This is what's part of the measure, and then there are different terms. And there is one term where I have 2 pi 4th delta 4. And it's easier if I draw first the diagram. So this diagram is what I would expect. In vacuum, I would say that if I compute the width of this phi, then it gives me the decay rate of the phi. So phi can decay into phi can decay into chi1, chi2. Chi2 had momentum p, chi1 I call the momentum q. This has the momentum k. So it should give something like this, k minus p minus q. And then, however, we get not 1. In vacuum we would get 1, but now we have to, and it comes out. That's the whole point of the computation. We get these Bose enhancements because here they are all bosons. And this is like Bose enhancement for, and now I simplify the notation. These are the Bose distribution for P and Q. So this is like Bose enhancement of this final state, but then there always must be the opposite process. So this is like this is one of the terms, and then there's the opposite, going in the opposite direction. And in that case, this would be the initial state. So minus NP and Q. But that's not everything. That's already like, if I omitted these, there would be 1. That would be the vacuum decay width. One can check that this is indeed, in that case, that it's the vacuum decay width of this phi, if the phi is heavier than the chi1 and chi2. Now it's thermally modified, but then there are also other possibilities. There are other channels which show up, and in fact, there are 2 other channels. And that's the kind of, in some sense, the key of the Boltzmann equation, also the strength of the Boltzmann equation. I didn't write it explicitly. We just have these sums over all these n and m particles, but really we have to take everything into account. So it's not only this phi which can decay, we can also pull these legs into the initial state. It's also allowed that this phi, it doesn't decay, but rather what we call inverse decay. In the thermal medium, we talk about inverse decay. This means that the phi actually comes together with the chi2 and forms a chi1. That is in principle there. Whether it's actually allowed depends on the masses of these particles, so one has to work it out. But if one just takes the imaginary part, then the structure comes out, namely the structure that now I would have k plus p minus q. And this would then be proportional to, now I have to find this p guy in the initial state. So it's proportional to the distribution of that p, and then the q is in the final state, minus, again, the inverse. Or I can instead pull the chi1 to the initial state. And so then it's k plus q must equal p minus p. And now it's the q which has to be in the initial state, and the p is in the final state, minus, again, the inverse process. Okay, so this really comes from this computation without any arguing. And this structure is exactly the structure of the Boltzmann equation. So this is then at least evidence that the Boltzmann equation, in a certain limit, it works. And so that's kind of the message I wanted to convey today. Boltzmann equation is just very important in cosmology. I don't think you can do cosmology for very many years before you are encountered with a problem where you have to solve a Boltzmann equation. And there's nothing to be afraid of in the Boltzmann equation, except that one has to always ask. It depends on the precision that you require. But if you are asking, is your computation really correct, or how precise it is, you have to question whether the Boltzmann equation is a precise description of that physics. And so at least we should have learned today that it's not wrong. I mean, there are limits in which the Boltzmann equation is correct. So usually in cosmology, at least it gives a reasonable first estimate. Okay, that's it for today. And tomorrow then we go from there, because then it turns out that often it's not enough just to do like one loop or so, but we have to do something like resummation. We have to start adding loops into our simple computation because there are big corrections from higher orders. For today, are there questions at this moment?
I was wondering about the initial states. So, if I remember correctly, you also assume that the initial states and final states are asymptotically free.
Yes, that's a good question. So the question is about the initial state, whether they are. So in QFT, one always assumes that in scattering that these states are some in states or out states. They are kind of they are free. They don't interact. And so here it's a very good question, because here you would find, if you made that assumption somehow a priori, you would find it very confusing. Because if you assume that these guys are in equilibrium, then for sure they are not asymptotically free. You cannot talk about equilibrium unless they interact all the time. So indeed, you shouldn't make that assumption, and you don't need to make that assumption. If you do this computation, you never did that assumption. You define something which is where you don't need to talk about asymptotic states. You carry out the computation, you take the imaginary part. It just so happens that afterwards you could give this expression an interpretation which resembles what we would have done in quantum field theory. But you shouldn't say that these guys are asymptotic states. They are not asymptotic states in a conceptual sense of something that doesn't interact. However, then on a deeper level, it comes back a bit to what I just mentioned, that at the end of the day, you also have to ask, I mean, these particles, maybe they interact still. And sometimes these interactions afterwards, they can be also important. And so then we have to start resumming. And so then it becomes a really good question. I mean, if you have to resum, then what should you do with your Boltzmann equation? Is it still valid, or do you just modify the masses by some thermal corrections, or you have to add other channels or so on? And that's like a really tough and good question. Yeah.
First of all, thank you for the lecture. So I have a couple of conceptual doubts, and the first one would be,
what is the reason behind, or the argument behind the expression you wrote for the gamma as the imaginary part of the self-energy?
So the question is, why did we write this expression? So of course here I didn't really justify it. I just could write it as a definition. Now, to justify why we talk about this kind of a guy, to justify it beyond Boltzmann equation, then what you do is this linear response theory, but then linear response theory not with Boltzmann equation, but linear response theory in quantum field theory. And this you can do just with operators and everything. And one has to define time orderings, and then one perturbs the system and looks at how it responds. And that's where the word response all comes from. Then one really talks about linear response in, well, quantum statistical physics or quantum field theory. And then that's where one can then understand why it's defined like this.
Then, so what is, because I got lost at some point, what is the relation between this gamma, which is derived from the imaginary part of the self-energy, and these production processes you wrote down there?
Yes. What is the relation of this gamma and these production processes? That's the question. And so the relation is, you don't need to make the relation. I just made this relation because that's an interpretation. So first you can just mathematically derive this thing, but it looks kind of a mess. So you want to give it some physical intuition. And then you realize that, okay, I can actually give this a physical intuition. And the wonderful thing about the Boltzmann equation is that it does have this physical intuition in terms of diagrams. So sort of afterwards I can reinterpret these in terms of diagrams. I just did it the opposite way, because then if you know the diagrams, it's easier to remember the structures. But if you did it actually, you would first get the expressions and then you give them an interpretation.
Okay, so this whole expression is derived from solving the summing problem.
Yeah, exactly, yes. You just do this, you can do it blindly, you can do it, you arrive at this expression. And then you can give it a physical interpretation. Well, first of all, you can check that it agrees with the Boltzmann. That's great. You can give it a physical interpretation, even independent of the Boltzmann if you wish. That's also great.